Introduction to Insertion Sort. So among many sorting techniques, we're gonna look into one of the simplest yet intriguing methods known as insertion sort. So it is very similar to the way many of us organize our thoughts or our physical spaces. We do this by placing each item in its rightful place, one at a time, ensuring order and harmony. So as we look into the intricacies of insertion sort, we will find out not only how it operates, but also where it excels and where it may falter. So let's try to understand the core intuition behind this sorting method. We can think of a sorting pile of book by weight, and each book represents an element in our array, and the goal is to arrange them in ascending order of weight, ensuring each book finds its place in the sorted section of our pile. Here is a pseudocode. So for each element in the array, you want to start from the second. What happens is you compare this element to the ones before it, because we want to compare this element to the ones before it. That's why we're starting from the second, moving each one step to the right until finding the correct position for the element, and then insert the element in its correct position. So, core concept of insertion sort. At the heart of insertion sort lies a straightforward yet effective strategy. What you basically is happening is you're iteratively expanding a sorted section at the beginning of the array by inserting the next unsorted element into its correct position within this sorted section. So imagine you're at a library with a stack of books to be shelved. If you're using insertion sort, you will start with one book, considering the shelf empty and thus sorted. As you pick up the next book, you want to slide it into its rightful place relative to the first book. And this process repeats with each new book compared to those already on the shelf, ensuring a sorted order is maintained. So this insertion sort, we can see that it's using in-place sorting, which means that no additional memory is needed beyond the original input array. So the elements are shuffled within the array itself, transforming chaos into order, one element at a time. Moreover, insertion sort is a stable sorting algorithm. What we mean by insertion sort being a stable sorting algorithm, the sort itself ensures the elements with equal keys, they retain their relative order after sorting is done. So, for instance, say two books weigh the same, but they are of different genres, then their order relative to each other will remain unchanged. So it preserves any prior sorting if it's done by genre. So as we traverse through, uh, for the example, pile of books, uh, you can see that insertion sort is very simple, and also it is pretty stable in a lot of scenarios, and is efficient in some scenarios. Insertion sort algorithm breakdown. So if we are to illustrate insertion sort by step-by-step execution, let's imagine you're sorting a row of plants by plant's height. Then you want to start with the second plant and you want to compare the plant to the first. If it's shorter, you move it before the first plant. So this is your new sorted section. You would then move to the third plant, comparing it backward through the sorted section. And you'll be relocating it to its correct position where it's no longer shorter than the plant before it. So this iterative comparison and insertion mimic the way we often organize items intuitively, by feeling out their correct position in an already ordered set. So the uh, core of this algorithm is this backtracking comparison, ensuring each element is inserted precisely where it belongs among the previous sorted ones. So when we are doing this process, we might encounter elements that are already in their correct positions. Uh, then you can see this algorithm's adaptive nature since it requires minimal movement. So you can see that uh, the insertion sort is pretty efficient with nearly sorted data. Efficiency and complexity analysis. So if we were to look at time complexity, space complexity of this algorithm, we can see that for the best case scenario, uh, elements are already in order or they are nearly sorted, then insertion sort performs really well with a time complexity of n. The reason why time complexity for best case scenarios of n is because each element requires a simple check to confirm its position. However, when we look at the worst case scenario, uh, example being the elements sorted in a reverse manner or they are heavily disordered, then insertion sort has to do a lot of comparison and shifts so that elements can go to its correct position. Therefore, it will have time complexity of n squared. In the average case, the insertion sort will have time complexity of n squared. And if we look at space complexity, insertion sort operates in place, which means there is no additional space required beyond the original array. Therefore, it maintains a space complexity of 1. Now let's talk about practical applications of insertion sort. Uh, Despite the limitation of uh, insertion sort actually finds its niche in the world of sorting algorithms. So There are hybrid sorting algorithms such as team sort, and team sort is used in Python's sorted function and also Java's array sort. So in team sort, insertion sort is used for sorting small arrays. It's because insertion sort is very efficient on small data sets, and so and there will be other sort applied if uh, the data set is large. So basically, as I said, in practical applications, insertion sort is used in Java's array sort and Python's sorted. So a lot of developers kind of recognize insertion sort's efficiency for small data sets. So if you already know that data set is small, you can use insertion sort. The advantages of insertion sort. I would say the main advantage of insertion sort is its simplicity. It's easy to implement and understand, and is really efficient for small or nearly sorted data sets due to its adaptive nature. And also, it is uh, stable, and its in place sorting makes it suitable for applications where stability and uh, in place sorting really matters. Disadvantages of insertion sort, I would say the insertion sort's performance significantly uh, decreases if you have large data sets, uh, and if the data sets disorder, then you be getting time complexity of n squared. This means that when compared to more advanced algorithms like quicksort or merge sort, insertion sort will be less efficient. That's it for insertion sort. Thank you, everyone.